Let's do double integrals in polar. You saw polar in Calc 2. It's the language that we used for r equals a function of theta. We did little heart-shaped things and rose-shaped things. Polar, we use it in Calc 3 a lot, because if we have a round domain, it is really tough to do a round domain with rectangular coordinates because the limits of integration have to have the, like let's say the radius of the circular domain is 4. Then you have to have y equals the square root of 16 minus x squared for the top limit of integration. And the negative square root of y equals square root of 16 minus x squared for the lower. It's annoying having such complicated limits of integration. Can make it really tough to do. So polar, if you remember, polar is an alternative to rectangular coordinates. You can still use an x-axis and a y-axis to draw stuff, but the method of location in polar is different. What you have is a number line, just like the x-axis, but it spins like a propeller at the origin. And you have some kind of function, some little function thing that's running along here. Positive number line, negative number line, running back and forth in here, laying down points as the angle changes. And that's how the curve forms. It forms as this propeller goes around, it forms in a circular method. So you can name a point. This point here, I went out 3 on the x, 3 on the y. That's the point 3, 3 in rectangular coordinates. It's also the point 3 square root of 2 comma pi over 4, because this angle is pi over 4, and the distance from the origin is 3 square root of 2. So it's an alternative way of laying down points. It's an alternative way of making curves happen. Because what's a curve? It's just a set of points. Now there's transformations that we use sometimes. You can have the transformation being, with x equals r cosine theta, y equals r sine theta. You can take x and y and turn them into r and theta stuff. If you already have r and theta, but you need to turn it back into x and y, which can happen, here's the moves for those. These guys get more use in Calc 3. We use these ideas more often. So we're going to do a Calc 3 double integral with a round domain. What it's going to be, it's as if you took a cylinder and shaved the top at an angle. So it's going to be a round domain with a tilted plane top. And we're going to find the volume of that figure, which would be tough to find otherwise. Let's see how it works. All right, so here's the first part. Here's the solid. I've got a tilted plane cutting off the top of the cylinder. The bottom of the cylinder is in the xy plane. I chose a radius of 2. So the domain is a circle centered at the origin, radius 2. I don't want to do that domain in xy coordinates. We're going to do the domain in polar coordinates. But here's what the integral would look like. The top surface is z equals. And here is this integral. We don't even bother to write in these limits of integration. I don't even write dy dx. But I do this. X is r cosine theta. Y is r sine theta. Plus 3 is plus 3. This little factor r on the end, it has to be there when you convert from rectangular to polar. You have to have an extra factor of r. Mandatory. We'll learn why like 3 or 4 sections from now in this chapter. But right for now, just remember to do it when you convert from rectangular to polar. In this section, this is 15.3, there are some integrals you just do them in polar, set them up in polar coordinates. Don't multiply by an extra r if it's pure polar from the start. It's when you have a rectangular idea, a rectangular start, and then you switch. Then you have to multiply by an extra factor of r. So here's what happens. I have, to multiply this by r, I'm going to have an r squared cosine theta. I'm going to have an r squared sine theta. That's 2 tabular integration by parts that we're going to do. We're going to do it and finish this thing up. Here we go. Did I say tabular? I'm an idiot. I'm sure that you stopped as soon as I said this. Hey, it ain't tabular because the theta is not the same variable as the r. I don't have to worry about it. All I have is, since this is dr, that cosine theta is like a 5. I'm just integrating r squared. I'm integrating r squared. I'm integrating 3r. Piece of cake. So that's the integration of the r squareds. There's the integration of the 3r. Evaluating from 0 to 2. So it's really just put in the 2 for each of these r's. So here we are. And now, how smart are you? Do you see? Enormous savings. Enormous work savings. Because the integral of cosine from 0 to 2 pi is net area 0. It's a full cycle of cosine. Everything cancels out. That's a big 0 right here. Same for sine. A full cycle of sine has net area 0. So my final answer is I don't have to do these integrals. I don't have to do them. They're going to be 0 anyway. But this guy, 6 times 2 pi, because this is going to be 6 theta. Theta goes from 0 to 2 pi. So it's 6 times 2 pi. In other words, the volume of this thing here is 12 pi. Not bad. And I would think that we might be able to come up with a little formula for these tilted plane problems, because this kind of move happens. I would think it doesn't happen just because of this one tilted plane. I think it happens a lot. Anyway, there's a good problem. Hope you dig it. So with polar, you're going to do dr d theta 95% of the time. Once in a while, you might turn it around to d theta dr. The thing that's interesting to look at is look at the limits of integration. 0 to 2, 0 to 2 pi. If you just look at this integral, just look at that integral without any picture of what it stands for. Just take r and theta as variables. This is a rectangular domain. It's a rectangular domain. It's just a number to a number. So you could rewrite this integral as a d theta dr just by switching these two integrals. You know, it would be 0 to 2 pi and 0 to 2 and d theta dr. Then since that thing wouldn't change. And you could do it, the double integral, in the opposite order. It wouldn't change the answer. You can see why that would be the case anyway. It's not going to change any of these moves. It's just it's going to change when they happen. But in general, it's kind of weird that we get a domain that was a round object. And in rectangular, it would be tough. We'd have a curvy set of limits of integration. But in polar, this circular domain becomes a rectangular domain because we're using a nonlinear transformation. And it happens to be, when you have a circular domain, the nonlinear transformation takes a circular domain in x and y and gives you a rectangular domain in r and theta, which I would do that trade in a heartbeat anytime. That's a much nicer domain. So there you go. That's your first example of a double integral in polar. 15.3, 7 through 19, try any odds you want. Talk to you later.